Good afternoon, everybody. So it's not easy to have a talk after close. Thank you. So thank you for the tectonic team of IPGP to have organized this meeting. It's super nice to be here. And today, as it's the end of afternoon, I will bring you in a travel into the past. And for that, we will go in Turkey. Where a Byzantine basilica has been discovered. This Byzantine basilica was discovered on the shore of the Lake Iznik. Here you have the city of Iznik, and maybe most of you know this city by its antique name, the Nicaea or Nicaea. It's the place of the first concile of Christianity that took place in this city. And the archaeologists were really excited by this discovery 10 years ago because they still don't know where the first concile has taken place. So they thought that it could be in this basilica. And I was super excited too because I was wondering how this basilica has been destroyed and sunken into the Lake Iznik. Because this basilica is located nearby a branch of the North Anatolian Fault that is following the southern shore of the Iznik Lake. And so I decided to do a project on this basilica, trying to have the calendar of seismicity, because I wanted to know the calendar of seismicity on this fault. And so I bring a lot of research in this project in order to have a pluridisciplinary approach with the tectonic group, with the people working on the lake study, because we will see that we have a lot of information about the calendar of seismicity into the lake, and also with some archaeologists. So today, as I don't have a lot of time, I will present you the result of the ANR Iznik secret using the lacustrine approach. So, as you probably know, the North Anatolian Fault is it's a plate boundary that separated Anatolia from Eurasia, that accommodated the westward motion of Anatolia. In this map of the seismicity of during the last century, you can see that almost all the segments of the North Anatolian Fault have been broken during the last century, unless 3 branches that are located on the western part of the fault. And in these 3 branches, there is a seismic gap. So in that part, the fault is subdivided into the northern branches that show the highest slipping rates, about 21 millimeters per year of slipping rates. And the 2 other ones, the middle branch and the southern branch, they have much lower slipping rate, something like 2.5 millimeters to 5, depending on the studies. So if we look now at the historical seismicity, what about the past seismicity? And so the chance in Turkey is that we have a lot of record of historical data, and there is a compilation of the past seismicity, and we can see that all the branches have suffered some earthquake during the past. So for the northern branch, the last earthquake was on the seismic gap was the 7066. For the southern branch, it's the 8055. And for the middle branch, so it depends. According to Ambrase, there was an earthquake in 1419 on the shore of the Iznik Lake. But for Guidoboni, this earthquake was rather nearby the city of Bursa. So there is also a discussion about the last earthquake on this branch. And we can see that during antique time, there were 6 historical earthquakes on this branch. And we don't know if the last earthquake was this one or another one that is described on the eastern part of the fault. As the area is occupied by people since a long time, there is a lot of erosion due to the agriculture, and the on-land paleoseismology have problem to date the paleo earthquake. So I decided to work in the Iznik Lake because it's preserved from erosion and from human impacts. And first, with Flavio and Selmeti, we did the bathymetry of 1/3 of the lake. And in this lake, we found 2 lineaments. The South Boyalicha fault, two active faults, in fact, and the Iznik fault that is nearby the Iznik city. We also observe, so the basilica is here, and we also observe some delta collapse and a nice lobe of turbidites. We can see them along all the shore of the lake. And so we decided to sample cores in this lake, and we found some turbidites. As Nicolas explained this morning, I will not explain again, but it's easy to see some turbidite in this lake. So we also have done some seismic reflection. So all this line, the yellow and the orange line, are seismic line. We have done a lot across the Iznik fault, and all the dots, they represent cores. So we have 30 short cores. They are the small dots on different parts of the lake. And the big orange dots, they are long cores that have been sampled thanks to the platform, the national instrument we have here in France, that INSU have, and we were able to have more than 90 meters of cores to study. So here is the map of the Iznik fault, and you can see all this seismic line. I will present you here one of the seismic line that is perpendicular to the fault. And we have 3 long cores, one in the footwall and 2 in the hanging wall. So here you have the seismic line, and you have the cores, the interpretation of the cores. So 2 in the hanging wall and 1 in the footwall. So the seismic lines show nice seismic layers that are separated here by the Iznik fault. We can see that there is an offset of these layers. And thanks to the cores, we have been able to correlate the seismic layer to the sedimentological layer. In the longest core, that are 15 meters long, and that encompassed 20,000 years, we can see that on the upper part of the core, we have a fine sedimentation, and we have been able to recognize a lot of turbidites. So all these lines, they represent turbidites. They have different color because there are different type of turbidites. So we have been able to observe more than 100 turbidites that are related to past regional seismicity. What we can observe also is on the bottom, so there is a hiatus in the cores. So in between 11 and 8,000 years, this area was emerged, and there were some erosion or non-sedimentation at least. And before, on the oldest part of the core, we have coarse sediments. That means the water level was very low, and we don't see any turbidite in that. We are not able to recognize them. So what we can observe also is that this hiatus, we also observe it on the footwall, and it's much higher. So we can see an offset of this hiatus, but also we can observe offset of the sedimentology, some of the sedimentological layers. And they are not only, so if you look at this pink layer, it's not only offsetted, but also there is a difference in the thickness of this layer. And so with that observation, we can definitely say that the Iznik fault has a vertical component, and it has ruptured several times. So, thanks to this layer, we have a chance to find the earthquake that occur specifically on the Iznik fault. I forgot, so which of all of these turbidites are related to the rupture of the Iznik fault? I forgot to say something super important, is that in all the cores, the last earthquake that have been observed is the one in 1065, and we know it's an historical earthquake that occurred on the middle branch of the North Anatolian Fault. And after that, there is no other turbidite. So if the layer are offsetted from both parts of the fault is due to the co-seismic effect. So imagine you have the normal sedimentation into the lake, and then you have an earthquake and an offset of this. An offset of due to the earthquake, co-seismic offset, and then you have the sedimentation just after, and you can see that the thickness of the sedimentological layer will be different in the hanging wall and in the footwall. And so, looking at all this layer, we have been able to propose at least 6 earthquakes that occur on the Iznik fault since 7,000 years. And when we are going toward the bottom of the course, we don't know if we are not losing some of the earthquake, but at least we have 6 during this time. And if we look at the 3 first earthquake, the recurrence time is almost 800 years, plus minus 100 years. And also we can have a vertical slip rate. So it's a very low vertical slip rate, but it's normal because it's supposed to be a strike slip fault. So it's 0.6 millimeters per year. But we also have the chance in the Iznik Lake to have recognized, thanks to the bathymetry, some paleo shorelines. So you can see them on this map. And we can also see, so these paleo shoreline, they correspond to we recognize them all around the Iznik Lake, and they correspond to the moment where the water level was very low at 11,000 years. And so we can see these paleo shorelines also with the seismic profile. And I don't know, it's not working. And so we can see 5 paleo shorelines. The oldest one is this one. Here it's a map of the paleo shoreline, and they are cross-cut by the Iznik fault. So if we zoom here, we can see, and so there is the crest of the paleo shoreline and the limb. And if we look carefully, the oldest paleo shoreline has been displaced from 24 meters, while the youngest one is offsetted by 6 meters. So thanks to this offset, we can have a horizontal slip rate on the Iznik fault of 3 millimeters per year. And the youngest paleo shoreline is about 3,500 years. And since that time, there have been 3 to 4 earthquakes. So if we consider 4 earthquakes, it's something like for each earthquake, there is a co-seismic offset of at least 1.5 meters. So the Iznik fault is probably is capable for big earthquake, maybe of magnitude close to 7. And what about all the other turbidite we found into the cores? So they are. So some of them are related to the other earthquake on the middle branch of the North Anatolian Fault, but some can also be related to earthquake on the northern branch and the southern branch. And thanks to this other turbidite, we can maybe resolve the question of the uncertainties on the location of the epicenter, past epicenter. And so for that, for each of the 70 earthquakes, we did a model with Céline Beauval and Jarod Domange. So for each of the earthquake, so first we took a simplified map of the fault. So for the northern branch, middle branch, and southern branch, here you have the Marmara Sea, the Iznik Lake is there, and here is the example of the map of intensity we have deduced. So we took the catalog of epicenter and of in macroscopic intensity magnitude that were in these catalogs. We defined rupture lengths based on this magnitude, thanks to the Timbanjian equation, and then we simulate the ground motion acceleration for each of the rupture. And we convert the acceleration into intensity for all the earthquake, and we look into the lake at the core place. What was the mean PGA or the mean intensity due to each of the earthquake? And so we have. I will show you the result on three cores, three short cores. The 21 that is nearby the Iznik fault, the 24 and the 27. So these cores are shorter, and they encompass. They show also that the very last earthquake, the last turbidity they show is the 1065 earthquake, and there are other earthquake like the 121 earthquake that was also on the middle branch of the North Anatolian Fault, and the 368, but all the other one, they are on other branches of the North Anatolian Fault. And so we have more or less the same, and we can correlate the different turbidite from each core. And so what we have looked is that as we have modeled each historical earthquake, we have looked at for the three cores. So the 21 is in blue, the 24 in orange, and the 27 in green. We have looked at the mean PGA for each of the earthquake, and the plain symbol represents the earthquake, the turbidite that have been recorded into the core, and the open symbol represents earthquake that have not been recorded into the core. In the x-axis, you have the age, so it's like a time series of the earthquake that have been recorded in the Iznik Lake. And in this axis, you have the mean sedimentation rate. And what we observe is that before the 1065 earthquake, the lake was able to record a lot of earthquakes, the earthquakes that are above a threshold that is specific for. That depends a lot on the sedimentation rate. And after the 1065 earthquake, no more earthquakes were recorded in the Iznik Lake because there is a drop down of the sedimentation rate. So if there is not enough sediment to feed the slope of the lake, even if there is some earthquake, there will be no record of turbidite into the lake. And so we thought that we can, if we put all the three cores together. So yes, during the 1065 earthquake, there was a huge purge of the sediment of the lake. And this earthquake have causes the destruction of the basilica. There are some texts that attest that. And so we put all the three cores together on the map that is showing the mean PGA and the mean sedimentation rate. The three colors represent the three cores, and so the earthquake that are so the PGA that are above this threshold, this line, are recorded into the lake, and we have tested the different epicenter of the 1490, so the epicenter of Embrasé and the epicenter of Guidoboni, and even with a low sedimentation rate, if the earthquake of 1490 occurred in the middle branch of the North Anatolian Fault, it should have been recorded into the cores. As it was not recorded, we prefer the epicenter location of Guidoboni et al. So also with this approach, we can have, if we know the sedimentation rate for any turbidite that we have recorded into the cores, we can know the intensity at the core location, and then for paleoseismology, for prehistorical data, it can be a very useful approach to know the intensity of earthquake, of prehistoric earthquake. So thanks to this study, we are able to say that the 1419 earthquake occurred on the middle branch of the North Anatolian Fault and not on this branch. The 1295-96 earthquake was not recorded also into the Iznik Lake. So the last earthquake that have been recorded is an earthquake that has its epicenter here and has propagated on the Iznik Fault. And so here is the compilation of previous paleoseismological data. Maybe I can just say that the youngest earthquake have not been recorded into the Iznik Lake. This one maybe because it's too small, and this one maybe was badly located, we don't know, or too small to be recorded into the lake due to the low sedimentation rates. But then this branch of the North Anatolian Fault is the place where the gap of seismicity is the highest. And if I do a brief scenario of the different earthquakes that occur on these branches, so this earthquake we probably occurred, but we don't record it into the lake. This one occurred on the southern branch, and the 165 that lead to the destruction and sunken of the basilica, it occurred from the middle branch of the North Anatolian Fault toward the Iznik Fault, and we don't have any trace on the southern branch. And the earthquake of 121 was a very big earthquake that has ruptured all the faults, even the Iznik faults, all along the North Anatolian Fault, and it was a 7.4 earthquake. So there were no equivalent earthquakes since 121 in this area. So I let you with that because I'm thinking I'm late. Oh, yeah. And if you want to know more about the history of the basilica and archaeological results, you can see the movie Iznik, the Mysterious Sunken Basilica. It will be diffused again in France 5 Télévision this year, because this year is the anniversary of the birthday of the First Council of Christianity. And so the Pope is going to Iznik, in this place of the basilica, to celebrate this council. And so probably it will be diffused again on PBS too.